Welcome to the 9th week of this course. In this week, we will discuss the concept of Baire spaces. So this is a class of topological spaces which have a variety of interesting applications within topology and especially in mathematical analysis. So what is the idea behind Baire spaces? So first, suppose that you have the plane R2, Euclidean plane, and suppose that you take the subspace L, which is a finite union of lines, straight lines, Lk. So suppose that you have finitely many lines, L1, say this is L2, this is L3, and say this is L4, and so on. And the idea is that if you take this union L, and if you take any point in this union, say in one of the lines, or it could be in the intersection, and you take an open neighborhood of this point, then there will be at least one point in this open neighborhood which will lie in L complement. So this point, for example, belongs to, say, P belongs to L complement. So here, for example, this point belongs to Q belongs to L complement. So every neighborhood, so given, I'll just write this down, given any point X in L and a neighborhood U of X, so U is an open set in R2 containing X, there exists a point Y in U such that Y belongs to L complement. So the idea, the Baire principle, if you want, Baire principle is that a union of thin sets is thin. So I'm putting thin in quotes, and we will make it precise what we mean by thin sets. And but now you have to put some condition on the type of union that you can consider. If it is an uncountable union, well, it's no longer true, because R2 can be written as the uncountable union of straight lines. So just consider each straight line, each vertical straight line for each x coordinate, and then R2 can be written as the union of Lx. So this is the vertical straight line passing through the coordinate x comma 0, and x if you take the uncountable union of all these Lx's, then you get R2. So now R2 is no longer a thin set, because this condition is no longer valid for R2. That given any point in X, given any point X in the union and a neighborhood U of X, there exists a point outside the set. So this is no longer possible for uncountable unions. So you must have countable unions, must restrict to countable unions. So we have seen that for finite union of lines, this is true. And the Baire principle says that a countable union of such lines, in abstract sense, they are called thin sets, and the countable union is still thin. And we will make this all of these ideas more precise using some ideas in topology, namely that of the interior of a set. So before we define Baire spaces, let us define what we mean by an interior of a set, and we will formulate the concept of Baire spaces using this notion of interior of a set. So okay, so let's define what is an interior. So this is the definition for the interior of a set. So if X is a topological space and A is a subset of X, we define the interior of the set A as follows. So we denote it as denoted int A, and it is defined as follows. So int A is equal to the union of all open sets contained in A. So it is the union of all open sets U, such that U is a subset of A and of course U is open. So this might remind you of the definition of a closed set, of the closure of a set, which was the intersection of all closed sets containing that set, and here it is the union of all open set contained in that set. So it is kind of an opposite thing to the closure, and in fact the interior of A is the largest open set contained in A. What do I mean by this? So similar to the closure being the smallest closed set that contains A, the interior is the largest open set contained in A, which means that if V is open and V is a subset of A. By the way, here whenever I say open, all of these are in X. Okay, so in X. So we are not considering A in the subspace topology, and we are considering all open sets to be in the topology on X rather than the subspace topology on A. So so if V is open in X and V is a subset of A, then V is a subset of the interior of A. So this is what we mean by a largest open set contained in A. Of course, interior A is already contained in A because you're taking a union of sets which are contained in A. Another point to note is that if A is already open in X, then the interior of A is just A. So similar to the fact that if A is closed in X, then the closure of A is A. Then this is the opposite notion, is that if A is open in X, then interior of A is equal to A. And we will use the concept of interior to define Baire spaces, but we make a terminology is that A is said to have empty interior if the interior of A is empty. Okay, so it's evident from the terminology what we mean. It just means that the interior of A is the empty set. Okay, so we will use this terminology a lot, and so I want you to understand what is the interior of a set and what we mean by an empty interior. Now, before we go to the definition of Baire spaces, let us give the relation between the closure of a set and the interior of a set, but for that we need yet another notion, which is that of the boundary, a topological boundary of a set. So let's define what is the topological boundary. So this is the topological boundary of a set. So sometimes we drop the word topological and we just say boundary. So what is the a boundary of a set? So let A be a subset of X, then the topological boundary or simply boundary of A, which is denoted by this notation delta A and is defined as follows. Defined as delta A is equal to the closure of A and intersection with the closure of the complement of A. So this is the boundary of a set. Now let us see some examples of interiors and boundaries for some subspaces of R. So for an example, if you take for example X to be R and A to be if you take it to be 0 1, the open interval 0 1, then the A being open, then the interior of A is A, which is 0 1, and the boundary of A, what is the boundary? So it is the closure intersection with the closure of the complement. So the closure of A is just the closed interval 0 1, and we take the intersection with the closure of the complement. However, the complement of 0 1 complement is already a closed set, so it equals the closure, and therefore this is nothing but minus infinity to 1. This is minus infinity to 0 included, union 1 to infinity. And so if you take the intersection with these with this union, minus infinity 0 included, union 1 to infinity, then you get nothing but the 2-point set 0 1. So this is nothing but the endpoints of the open interval. So this is 0, this is 1, and the boundary is the usual boundary that we have the geometric intuition for. So for nice spaces, our geometric intuition gives us the right answer for the boundary. However, for some subspaces, the boundary can actually be larger than the space itself. So for example, if you take X to be R and A to be the rationals, then the interior of A, this is going to be empty, because if you take any point in the rationals Q and you take any neighborhood AB containing it, then that neighborhood must have an irrational point, and therefore there is no open set inside Q. Therefore the interior of this set is empty, and so Q has empty interior in our terminology. Now let us look at what is the boundary of this set. So this is nothing but the closure of Q intersection with the closure of Q complement, but this is nothing but the closure of Q intersection the closure of R minus Q, and we know that any point on the real line, and if you take any neighborhood AB of that point, then it must contain at least one rational, well actually infinitely many, but at least one rational Q and at least one irrational, say alpha. Okay, so Q alpha is an irrational, alpha is an irrational, and Q is a rational. So this means that every real number belongs to the closure of both the rational numbers and the irrational numbers, and therefore both these closures are actually equal to the real numbers. So R intersection R, but this is nothing but R. So in this case, the boundary of the rationals is actually the whole of R, and so in this case the boundary is actually larger than Q itself. So we have to be careful with the intuition and our mathematical definition. Sometimes they don't match up, and you get results which are counterintuitive. Okay, so now that we have the boundary, now the following theorem gives you the precise relation between the closure, the interior of a set, and the boundary of a set. So this is our theorem. It says that if you take a subset A of a topological space X, then we have two results. First one says that the interior of A and the topological boundary of A are disjoint, and the second one says that the disjoint union of interior and the boundary gives you the closure. So these are the relations between the interior, the boundary, and the closure of a subset. So let us look at the proof of this theorem. So for one, note that a point X does not belong to the interior of A if and only if for every neighborhood U of X contains at least one point in the complement of A. This is because if there are no points in the complement of A, then U must be an open set contained inside of A, and therefore X must be inside the interior. So therefore every neighborhood must contain at least one point in the complement of A. So now let X belongs to the boundary, topological boundary of A. Now this means that X belongs to, so this is by definition the closure of A intersection, and so this is just an and X belongs to the closure of the complement of A. This means that so just from the second part, this means that every neighborhood of A intersects every neighborhood of X, every neighborhood of X intersects the complement of A by the neighborhood characterization of a point in the closure, and this means that X does not belong to the interior of A, and this means that the intersection of these two sets is empty. And for the second one, for 2, we already have that the intersection of A union the boundary of A is a subset of the closure of A. Since the intersection of A is a subset of A, which is a subset of A closure, and the boundary of A is the intersection of A closure and the closure of the complement, and this is also a subset of A closure. Therefore the union is a subset of A closure. So it suffices to show that A closure is a subset of the interior of A union the boundary of A. So to show this, we will show that if X belongs to the closure of A and X does not belong to the interior of A, then this implies that X belongs to the topological boundary of A. Now since since the topological boundary is the intersection of the closure of A and the closure of the complement of A, it suffices to show that if X is in a closure and X is not in the interior, then X belongs to the closure of the complement of A. So why is this true? So since X is not in the interior of A, this means that every neighborhood of X intersects a complement, and this means that X belongs to the closure. So simple enough. So if you take a point which is already in the closure, but if you leave out the interior, then it must belong to the closure of the complement. So this proves the result. And now we will formulate the concept of Baire spaces in terms of closed subsets with empty interior. So this is the definition of a Baire space. So a topological space X is called a Baire space if it satisfies the following condition. So the condition is that given any countable collection AN of closed sets in X with empty interior, so each of these AN satisfies that the interior of AN is empty for all N, then the union of all these closed sets with empty interior also has empty interior. So in our example, so let me go back to the example that I was giving at the beginning of this lecture about straight lines in R2. So for finitely many lines in R2, it is quite easy to show that first of all, each line has empty interior. It is a closed subset of R2, and the union of finitely many such lines also has empty interior, because geometrically, as I showed, it is evident that there will be a point in the complement. So however, to talk about countable union of arbitrary closed sets, not just straight lines, this is perhaps not so obvious for even for R2, that the union will still have the property that it has empty interior. So if you take a countable collection of closed sets with empty interior, it's not quite obvious that the union of those sets will also have empty interior. And this is what the concept of a Baire space is. And the main result, the main theorem that we want to show, which is called the Baire Category Theorem. So this is our goal for this week, to study Baire spaces and to prove the Baire Category Theorem. And it says that if X is a compact Hausdorff space, or if X is what is called a complete metric space, then X is a Baire space. So in particular, each Rn, even though it is not a compact Hausdorff space, it is a complete metric space. So Rn is a complete, I will define these concepts a bit later, is a complete metric space for all n greater than or equal to 1. And so in particular, Rn is Baire. Rn is a Baire space for each n. And therefore, in particular, if you take R2, then any countable collection of closed sets with empty interior will have the union also having empty interior. We will prove this Baire category theorem in the next couple of lectures, and we will also show that in particular that Rn is a complete metric space. We will define what is a complete metric space, and we will show that Rn is a complete metric space, which by the Baire category theorem will imply that Rn is a Baire space.